V3 and V4, you'll get it as an I1 double dash as I have explained this by the circuit diagram. So this comes like I1 double dash is equal to 2 amps, I2 double dash is equal to minus 4 amps, I3 double dash is equal to 6 amps, I4 double dash is equal to minus 6 amps. Now we need to find out the actual current. So actual current I1 should be equal to I1 dash plus I1 double dash. I2 should be equal to I2 dash plus I2 double dash, and so on and so forth. So if you add up actual current of the circuit, adding the currents due to both the currents and the voltage source, then we will get as an I1 is equal to 17 amp, I2 is equal to 6 amp, I3 is equal to 11 amp, and I4 is equal to minus 1 amp. So to find out the current in this particular each branches I1, I2, I3, I4, what we did is we have kept this as an open current source, and we have found out the new currents in the each branches as an I1 dash, I2 dash, I3 dash, I4 dash. Then for the second part, we have removed this voltage source, saying that it's an open voltage source. Okay, and then we have found out the I1 double dash, I2 double dash, I3 double dash, and I4 double dash. So according to the superposition theorem, it should be the vector sum of the current which is caused separately. Then we said that I1 was equal to I1 dash plus I1 double dash, I2 was equal to I2 dash plus I2 double dash. So in that manner, we have found out by using the superposition to that particular given network circuit, we found out the value of each current in each particular asked branch. So we found out the value of I1, I2, I3, and I4. So this was all about superposition theorem. Now Thevenin's theorem. The next theorem is called as a Thevenin's theorem. The statement for Thevenin's theorem is any combination of voltage sources, current sources, and resistors with two terminals is electrically equivalent to a single voltage source V and a single resistor, series resistor R. See, unless we see the circuit diagram, we may not immediately follow up the statement, but once we prove it using a linear network circuit, again I'll go back and again I'll repeat the statement for the Thevenin's theorem. Any two terminals linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source in series with a voltage resistor. So basically what the Thevenin's theorem is saying as any linear network can be replaced with a single voltage source in series with a single resistance. So this is how it looks like. Okay. The Thevenin's equivalent circuit provides an equivalence at the terminals. Okay. The two objectives, important objectives are provides a way to find any particular voltage or current in a linear network with one or two or any other number of sources. More focused or more considered a specific portion of a network by replacing the remaining network with an equivalent circuit. How the calculations are done for the Thevenin's equivalent. Sequence to proper value of RTH and ATH. RTH is nothing but Thevenin's resistance or impedance, and ATH is nothing but Thevenin's voltage. So we will hereafter abbreviating the equivalent voltage and equivalent resistance, whatever we get it, as an ETH and ZTH or RTH. Okay. So the steps to be followed up for finding out the values of ETH and ZTH. The first is remove that portion of the network across which the Thevenin's equation circuit is to perform. In the figure below, this requires that the load resistance RL be temporarily removed from the network. So here, if you see, this is the load resistance, this is a single source, and R1, R2, and R3. Got it? So we need to remove this particular load resistance. we need to label these two terminals and terminals as we have labeled here as an A and B, and remove this particular load resistor. Mark the terminals of the remaining two terminals network, like as we labeled it as an A and B. And to calculate RTH or ZTH, by first setting all sources to 0, voltage sources are replaced by short circuits and current sources by open circuits, and then finding the resultant resistance between the two marked voltage. It means we need to short circuit this one, okay, and find out the value of the total voltage at these two particular terminals which we have labeled it. And for ETH, calculate ETH by first returning all sources to their original position and finding the open circuit voltage between the marked terminals. This can be called as a Thevenin's equivalent circuit with a single voltage source as an ETH with a single resistor RTH which is in series with this particular voltage. Draw the Thevenin equivalent circuit with the portion of the circuit previously removed, replaced between the terminals of the equivalent circuit. So this was earlier, this load resistance was previously removed, and again we have considered and drawn this particular load resistance between these two terminals. And this step is indicated by the placement of the resistor RL between the terminals of the Thevenin's equivalent circuit. So now we need to find out the current passing through this particular load resistance RL. So instead of finding here, so this is a circuit, the current through this particular load resistance we have labeled it as an IL. So this linear circuit can be replaced with a single voltage source in series with a single resistance as shown in this particular diagram. So this IL, which is in this particular equivalent circuit, should be equal to this particular IL, which is flowing in this particular linear circuit. So then we can say that the Thevenin circuit or the Thevenin's theorem is proved. Let's see the statement once again. Any two terminals of a network containing sources of impedance and linear impedances can be replaced by an equivalent circuit consisting of a voltage source ETH in series with an impedance ZTH. The EMF of voltage source is equal to the potential difference between the two terminals in open circuit position. The series impedance is equal to the impedance between two terminals when all sources being replaced by their internal impedances. So what it is saying that any linear network can be replaced with a single voltage source in series with a single impedance. Now, so how we will find out the value of ETH and ZTH, and then we will prove that the current through the load resistance, like here, just please look into this particular circuit, figure A. This is an EMF E, its internal resistance is R, and this is impedance Z1, Z2, and between these two terminals we have a load impedance ZL. This is the current I1 in this direction in mesh 1. This is an I2 in mesh 2 with this shown direction. Okay, so both we can say they are into a clockwise direction. So it contains, if you see this figure A, it contains a DC source of EMF E of internal resistance R. Z1 and Z2 are the two impedances connected in series with the source. And A and B are the terminals of the network, and the ZL is the external load. Okay. Now, first, what we need to do with the load terminals A and B open. So just go back and see this particular new figure circuit shown in figure 15B. What we did these two terminals as an open. It means we have removed this load resistance ZL and kept these two terminals as an open. So on that condition, we calculate the open circuit EMF of the voltage, that is ETH. So this voltage between these two open terminals A and B will give the equivalent Thevenin's voltage. It means we are finding out ETH. So to find out the value of ETH, we have to make the terminals A and B open and remove the load resistance ZL. So this is how the new circuit have come up now. So what is the current? What is the current in this particular circuit? I should be equal to, according to Ohm's law, what? I should be equal to V by R. So what is I? What is E or V? V is nothing but E. So it should come like, now we can see that this internal resistance, Z1 impedance and Z2 impedance, these three resistance are in series with respect to this particular source as an E. So the current in this particular circuit B of 15 figure, I is nothing but E by R plus Z1 plus Z2, because if the resistance are in series, then the resultant resistance will be equal to R1 plus R2 plus R3 and so on. If the resistance are in parallel, then the resultant resistance is nothing but 1 by R should be equal to 1 by R1 plus 1 by R2 plus 1 by R2. So using that, we can say that the current is equal to E by R1 plus Z1 plus Z2. Now what we are finding out the voltage across these 2 points. So what is voltage? V is equal to I into R. R is what? Across this particular impedance Z2. So we can say that I into Z2 is nothing but ETH, isn't it? So that is nothing but ETH will be equal to current into impedance. And what is the current? From here, current was E by R plus Z1 plus Z2 into Z2. So this is how we could find out the value of ETH or equivalent voltage source. As it is Thevenin's equivalent, it is labeled as ETH. Now what is the next we need to find out? We need to find out ZTH. And for that, what we need to do? We need to remove the battery. If you see the figure C of 15th diagram, so this is C circuit diagram of figure C. See, here we have removed the source E, isn't it? So this is only considering its internal impedance R, internal resistance R. This is Z1 and this is Z2. And this, as usual, this we have to keep it as an open. So the battery is removed while its internal impedance R is considered. Corresponding to point A and B, Z1 and R in series. So with respect to point A and B, this internal resistance and Z1 are in series, and equivalent impedance resultant, I mean, like, you know, this resultant impedance is in parallel with this particular Z2 impedance. So R plus Z1 is the equivalent of this two particular resultant resistors, because with respect to the terminals A and B, these two are in series and resultant resistance is in parallel with Z2. So according to the formula, if the two resistors are in parallel, then the resultant resistance will be equal to 1 by R1 plus 1 by R2. So this is the resultant impedance ZTH. So 1 by ZTH should be equal to 1 by R plus Z1 plus 1 by Z2. So we can see the mathematical expression. This is the two resistance as they are in series with each other. So equivalent Z is equal to R plus Z1. And as between the two terminals, we are finding out the equivalent impedance ZTH. So 1 by ZTH should be equal to 1 by Z2 plus 1 by Z1 plus ZR. So if you calculate this, so ZTH we got it as an R plus Z1 into Z2 divided by small r plus Z1 plus Z2. So we just label this ETH as an equation 1 and ZTH as an equation number 2. So this is a Thevenin's equivalent circuit, where which we have a single source with a single impedance which is in series with this particular source, and between these two terminals we have connected a load resistance ZL, and we will be finding out the value of load resistance I through ZL. So what is now I? The current flowing through this particular resistance should be equal to what? As we say, Ohm's law is V is equal to IR. I should be equal to V by R. So this current which is flowing through the load resistance should be equal to ETH by ZTH. Okay, so the current through the load resistance, whatever we label it as an I2, that was equal to ETH by ZTH, where ETH is this value and ZTH is this value. If you could find out the same current, okay, this is labeled, this current is labeled as an I2. So the I2 is the current flowing through this particular network circuit through the ZL. So this I2, whatever the value, if you found that this I2 is equal to ETH by ZTH, then we can say that the theorem is proved. Okay. So now we have changed this particular circuit into an equivalent circuit, which looks like this. And we are now going to prove the Thevenin's theorem, where which we will say that the current through this particular load resistance in a linear network, here I2 is equal to ETH by Z2, ETH by ZTH. Now this is a proof. Okay, so we will consider this particular main diagram, the figure A, and we will say that this is a mesh 1 and this is a mesh 2, and applying Kirchhoff's voltage law to mesh 1 and mesh 2 individually, we will get the two equations, and that two equations comes like this is I1, so I1 into R plus Z1 plus Z2 minus, as these two are into clockwise direction, it means the I2 is the current which is moving in this opposite direction. I1 is in this direction and I2 is from down to up. So the equation comes like E is equal to R plus Z1 plus Z2 into I1 minus Z3 into I2. Okay, this is the first equation. And for the second one, it will come like, how it comes like? It comes like I2 into ZL. This is an I2. So I2 into ZL plus I2 into Z3 minus I1 into Z3 is equal to 0, because there is no source in the second mesh. So if you rearrange the equation what I said now, we can write it in form I1 and I2. So this comes like R plus Z1 plus Z2 into I1 minus Z2 into I2 is equal to E, and second equation comes like Z2 plus ZL into I2 minus Z2 I1 is equal to 0. Okay, so if you can see here from this particular equation 4, you can find out the value of I1 if you transfer it into the right hand side. So here, from here you can say that I1 is equal to Z2 by plus ZL by Z2, okay, divided by into I2. So this is how it's coming like I1 is equal to Z2 plus ZL by Z2 into I2. Okay, now substituting the value of I1, again go back here and substitute the value of I1 in equation number 3. So if you substitute it, how it comes? R plus Z, because we are finding out the value of I2. I2 is the current which is flowing through the load resistance. I2 is the current which is flowing through the load resistance. So we are finding out I2. And if this I2 comes like ETH by ZTH, we can say the theorem is proved, isn't it? So that's how we are doing this mathematical calculations. So substituting the value of I1 in equation number 3, so it comes like R plus Z1 plus Z2 into, this is Z2 plus ZL by Z2 into I2 minus Z2 into I2 is equal to E. So if you take I2 as in common from this expression, so if you take I2, so the remaining factor will be R plus Z1 plus Z2 into Z2 plus ZL, okay, and this is denominator is whole divided by Z2 minus here only Z2 is equal to E. Then, so what we are doing is, we just took this I2 as an E by this complete fraction. So I is equal to V by R. So I2 is equal to V by this complete fraction. Or what we did is E by, we have multiplied this into Z2 by R plus Z1 plus Z2, because this is a denominator, this Z2 will go into the numerator, so this will come like E into Z2, and then we have divided the same equation E into Z2 divided by R plus Z1 plus Z2. So that what happens is here R plus Z1 plus Z2 can be cancelled. So the remaining factor will be Z2 plus Z1 minus this is because we have multiplied by Z2. This is Z2 square divided by R plus Z1 plus Z2. Got it? So the numerator part as it is we are written the same E into Z2 by sorry, this R only one R is over there. This is just a print. So Z2 by R plus Z1 plus Z2, and the denominator is nothing but how it is coming like here we have taken Z2. This is as it is Z2 minus this expression Z2 square by R plus Z1 plus Z2. Okay, plus ZL. So this is how we have written. We are rearranging every factor only to see that the final expression it should come in the form of ETH and ZH equation, which we already found out in the equation number 1 and 2. Okay, so this is the numerator part as it is. Again here we have taken as in Z2 as in common. So this is Z2 common. So this comes like 1 minus Z2 divided by R plus Z1 plus Z2. This is as usual ZL. Again the numerator part is same. So here I can say that if I take Z2 as in common, and if I cross multiply this, and if I do the subtraction of Z2, so the numerator part for this particular factor will be R plus Z1 divided by R plus Z1 plus Z2 plus Z3. So this we label it as an equation number 5. So if you see the numerator of the equation number 5 as an E into Z2 by R plus Z1 plus Z2. So if you compare this and see this equation number 1, E into Z2 by R plus Z1 plus Z2. It means equation 5 numerator, this part is nothing but ETH. Similarly, denominator of equation 5 is this fraction Z2 into R plus Z1 divided by R plus Z1 plus Z2 plus ZL. So let's go back and see the equation number 2. So what is ZTH? ZTH is Z2 into R plus Z1 divided by R plus Z1 plus Z2. So the same thing, you got it as in this as an ETH. So this is nothing but I2 is equal to what? ETH by ZTH plus ZL, because we are finding out the current across the load resistance. So this is an equivalent circuit, ETH and ZTH, and these two are in series with each other, and we are finding out the current through this particular load resistance. So the current through this particular load resistance should be equal to ETH by ZTH plus ZL. So this I2 we got it as an ETH by ZTH plus ZL. So from equation 5 we get it as an I2 is equal to, this is ETH by ZTH plus ZL. So very clearly by comparing equation 1 and 2 with equation 5, we can say that it is the same values what we got it as, and we can say that the theorem is true. So I2 is equal to ETH by ZTH plus ZL. So it means any equivalent circuit according to Thevenin's theorem can be replaced with a single voltage source as ETH in series with a single resistance as RTH. So this is all about the Thevenin's theorem. Let's see an example and apply a Thevenin's theorem to a linear network and find out the values of current in the circuit. So this is an example. We have taken a circuit. This is 5 ohm, 20 ohm, a voltage source of 25 volt, and this is a current source 3 amps. This is a 4 amps, 4 ohms, okay, and these are the two terminals labeled as an A and B. We can say it is an open. So in order to find the Thevenin's equivalent circuit for the circuit shown in figure 1, calculate the open circuit voltage VAB. So this is an open circuit voltage because these two terminals we kept it as an open, and these two terminals we labeled as an A and B. Note that when the terminals A and B are open, there is no current flowing through this particular 4 ohm resistance. If this is open, obviously there won't be any current across or through this particular branch. So that is 4 ohm resistor. Therefore, the voltage VAB is same as voltage across 3 amp current source. It means the voltage across terminals A and B is nothing but the voltage across these 2 points. In the sense, across this particular 3 amp current source, labeled as an V1. To find the voltage V1, solve the equation for the singular node voltage by choosing the bottom right node as a reference. So the same way we did it already. So this comes like how much? If you see this, this V1 should be equal to what? 25 minus 5. V1 should be equal to what? Sorry, I should be equal to what? V1 minus 25 divided by 5. So this is nothing but V1 minus this voltage. We say this is in B. So V1 minus B divided by R1. Okay, plus V1 divided by, what is this? R2. Plus, what is that? Already, as we said that the node voltage we need not to assign if the value is given. So was plus, what is that? 3. So how the expression comes like V1 minus 25 by 5 plus V1 by 20 minus, what is the current value? Minus 3 should be equal to 0. The summation of all the voltage should be equal to 0. So if you see this equation, you'll get it the same one. What I was saying, V1 minus 25 by 5 plus V1 by 20 minus 3 should be equal to 0. And if you solve this equation, you will get V1 as an 32 voltage. 32 volts. What is the next step? The next step is to short circuit the terminals and find the short circuit current for the circuit shown in figure B. Note that the current is in the same direction as falling voltage at the terminals. So now what we did is, we have short circuit the current. Here you can see that short circuit current. We have shorted this particular terminal A and B. So we can say that the current through this particular terminal now is considered as an ISC, nothing but a short circuit current. So current ISC can be found if V2 is found. Now if we have the value of V2, we can clearly say that V is equal to ISC is equal to V2 by R. So what we need to do, by using the bottom right node as a reference node, the equation for V2 becomes, so please look here, let's go through this. It will become like, this is V2, right? So the expressions comes like V2 minus 25 by 5 plus, okay, V2 minus 25 by 5 plus V2 by 20 minus, this is 3, they have given minus 3, okay, minus 3 plus V2 by, this is 4. So how the expression comes like V2 minus 25 by 5, V2 plus 20, this is a minus 3 amps, plus V2 by 4. So summation of all those voltage should be equal to 0. Now please look here. The same one, V2 minus 25 by 5 plus V2 by 20 minus 3 plus V2 by 4 is equal to 0. So if you solve this, you'll get V2 as an 16 voltage. Okay, so what is the short circuit voltage, short circuit current now? From here, ISC will be equal to what? V2 by 4. So it comes like 16. We got it V2 as in 16 volt. So 16 by 4 is nothing but 4 volt. So this is ISC is equal to 4 amps. So what is Thevenin's resistance? ZTH should be equal to VTH, the total voltage by the total current. So this is 32. You can see here, this is 32 divided by 4. You got it as an 8 amp. And this is nothing but Thevenin's equivalent circuit. So this is how we can find it out, applying superposition theorem to a linear network. Now the next is called as in Norton's theorem. So Norton theorem for a linear electrical networks states that any collection of voltage sources, current sources and resistors with two terminals is electrically equal to an ideal current source I in parallel with single resistor. So it is just as simple as the Thevenin's equivalent circuit. In the case of Thevenin's theorem, we said that any linear network can be replaced by an equivalent voltage source in series with a current source. So whereas in the Norton, any linear network can be replaced by an equivalent circuit consists of a current in parallel with resistance. So there in the case of Thevenin's, we have taken as an ETH in resistance in series with a ZTH. Whereas in the case of Norton's theorem, any linear network can be replaced with a single current source in parallel with a single resistor. So as that was defined as an ETH and ZTH, here we will be saying this is an IN and RNO or RN. Okay, so this is how the equivalent Norton network for any linear network circuit. So to calculate IN and RN, remove that portion of the network across which the Norton equivalent circuit is found. Mark the terminals of the remaining two terminal network. Okay, and to find out RN, calculate RN by first setting all sources to 0 and then finding the resultant resistance between the two marked terminals. So this is one. And IN, how to calculate IN in the circuit. First, returning all the sources to the original position, because earlier we have made it to short circuit. So returning all sources to the original position and then finding the circuit, the short circuit current between the marked terminals. It is the same current that would be measured by an ammeter placed between the marked terminals. So what is the conclusion? Draw the Norton